welcome to our webinar on the evolution of next generation data center networks. This is the fifth in a series of webinars that we've been doing. They're sponsored by DuPont Silicon Valley Tech Center and the Consortium for Onboard Optics, or COBO. So we're really fortunate today to have two distinguished guests with us from two innovative companies in this space for next generation data center networking. First, we'll hear from Amit Sanyal, who is VP of Marketing at Innovium. Previously, Amit was Executive Director at Dell, and during his 5-year tenure there, he drove networking solutions for the data center. Amit also spent 11 years at Cisco, managing marketing and product management teams in routing, switching, and servers. Earlier in his career, he was at Sun Microsystems. Amit holds an MBA from the Wharton School and a BS in Computer Science and Engineering from the Indian Institute of Technology, Delhi. So Innovium, for those of you who might not be aware, is a super hot Silicon Valley startup specializing in programmable switch silicon for cloud and edge data centers. And so why the excitement around this company? Well, they've brought to market several generations of their switching technologies and immediately made inroads at some of the top cloud providers. In fact, we should also note that last year, in 2020, they shipped over 1,400,000 switch ports. Really quite an achievement. Joining us today is also Hugh Durden, who serves as Inphi's Vice President of Marketing, Networking, and Interconnects. Hugh joined Inphi after the company acquired eSilicon in 2020. Prior to eSilicon, Hugh was at Cadence, and before that, at Xilinx, Altera, LSI Logic, and Digital Equipment Technology. Hughes holds a BS in Computer Science and Engineering from Rensselaer. Inphi, by the way, was in the news yesterday. Marvell just completed their multi-billion-dollar acquisition of Inphi, which is, of course, well known for its optical interconnect solutions, its DSPs, including its new 400ZR implementations. So with that, we're just about ready to get started. During the webcast, all the participants will be in a listen-only mode, but we certainly encourage your questions. Please use the chat function to do that, and we'll go through those questions at the end of the presentation. Of course, please focus your questions on the material that's being presented, next generation data center architecture, and not on financial matters or other things out of the scope. So with that, we have 1 hour for the webinar, and we have lots of great material to cover. Let's turn it over to Amit, and let's get started.
So thank you, folks, for attending. First, we are going to talk a bit about the evolution of network architecture. We'll take a look at the historical view over the last 20 years or so. Then we look at the key drivers that are impacting networks. We look at requirements as a result of that. And then we will look at the solutions that we are collectively developing in the industry, both from a switch as well as from an optics perspective. Now, let's first look at a little bit of the historic view. If you look at over the last 20 years or so, we'll look at how data center network have evolved. We'll focus on who the key leading customers were. They were driving key requirements. We look at the size of the data center, what type of servers they deployed, what types of NICs, network connections they had, and as well as the architecture that these data centers had and the types of switches that they deployed. So if you start from the 2000 onwards, key customers that were driving requirements and drove majority of the revenues were the financials and the Fortune 100. Around 2010 is when cloud started to emerge. And today, it's the cloud customers that drive a significant portion of the revenues and the requirements, and along with edge, of course. The size of the data centers back around 2000 were fairly small, definitely somewhere in the thousands, less than 5,000 servers in any location. it continued to grow. And at that time, the servers were a mix of RISC, Sun and HP RISC servers. x86 was just emerging. And fast forward to today, you have over 100,000 servers in one data center. Of course, the edge data centers are smaller, but the cloud ones have over 100,000 servers. And it's got a mix of x86, that is the predominant, but then there is ARM, and then more recently, new set of AI servers that include GPUs, AI accelerators that have emerged. In terms of network connectivity, the servers had mostly 100 meg back around 2000. 1 gig NICs were just emerging at that time. The network connections were mostly gig. Now, the bandwidth, of course, kept increasing. Today, we have predominantly 25 gig to 100 gig, and in some cases, even 200 gig NICs. Network connectivity is in the range of 100 to 400 gig, depending on the size and scale or the type of customer. The network architecture itself, it was 3 tiers even back in 2000. It was used to be called Access Aggregation Core. All 3 of them were chassis, and Catalyst 6500 was pretty much the de facto standard for many of these enterprises. Okay. In around 2005 is when the first top-of-rack switch came around with Catalyst 4948. It changed the landscapes. Ever since then, most customers have been deploying top-of-rack. And around 2010 is where really the arrival of merchant silicon happened. And since then, merchant silicon has been driving many of these data centers. And as you can see, now most of the leading data center customers are deploying fixed switches in all the tiers. The name now is called top of rack, TOR, leaf and spine. So leaf and spine is what people call, and you may have multiple tiers of leaf and spine. Now let's look at how cloud data centers are set up. There are multiple regions in the US and the rest of the world. Within a region, you have multiple availability zones, and availability zones are there for resiliency purposes. So in case of any disaster, if one availability zone gets impacted, the other should be up. So typically they are far apart. Within one availability zone, you have multiple data centers or buildings. And if you look at each data center or a building, the network architecture typically looks like the following. You have servers and storage set up in racks, and you have hundreds of these racks in a data center. These racks are often set up as pods. So a collection of racks are called pods. On top of each rack, you have either one or a pair of top of rack switch, and that is used to connect the servers and storage to the network. And then these top of rack switches are connected to the fabric, the network fabric, through leaf and spine switches. The one thing is I show a number of leaf and spine switches. The number could vary depending on the size and scale of the data center. And each one of these leaf and spine could comprise of a number of switches set up in a class to be able to create a larger radix switch. Okay? So different customers use different radix switches in the leaf and spine. Connecting the data center to the outside, you typically have internet-facing routers. They have most of the internet routes, and you're able to go to the ISPs outside. And then connecting between the data centers or the buildings is what we call as a DCI, data center interconnect set of switches that connect to other buildings. This is the private network that connect the various cloud data centers. Let's look at some of these in actual customer deployments. So here is Facebook's F16 Fabric Design. Okay, you can see here this data center has 4 buildings. Each one of these buildings are the size of a football field. If you look at expand the network architecture within one of these buildings, you will see that there are these rack switches that are the top of rack. These are Wedge 100S. Their configuration is 32 by 100 gig. So they connect to servers and storage within the rack, and they have 16 fiber pairs going out, connecting to the leaf and spine planes. There are 16 spine planes. Each of these spine planes have 36 spine switches. And so these leaf and spine switches, what they are 128 ports of 100 gig based on a single ASIC design. The switches are called mini pack. And you can see that a number of these racks, 48 of them, in fact, make up a server pod, as we were showing earlier. Let's also see another customer. This is Google. Google was an early adopter of merchant silicon and developed their own switches. They have developed many generations of switches. And you can see again that they have racks that there are so many racks here. On top of every rack, there's a top of rack. Then they have an aggregation, edge aggregation block. So this is similar to the notion of a pod. Connecting these blocks to the spine, they connect through either through the generation of these data center switches. They've moved from 10 gig to 40 gig to 100 gig to 200 and 400 gig. And they are looking to go to the next evolution, which is 800 gig next, and then further looking at 1.6T, even looking into the future. Okay. Now, let's take a look at future drivers of the drivers that will drive network requirements in the future. So the first thing we'll look at is applications and the new application architectures. Second would be how compute and storage is evolving and how that is driving networks. Third, we'll look at evolution of AI and machine learning. This is making a big impact on the network. And then huge amount of focus on power. So we'll look at how power is influencing network architectures, and then size and scale. Let's start with applications and application architecture. No longer do people write monolithic apps. They are writing cloud native applications using microservices, and where they use containers. So the application is broken up into various services called microservices, and each one of those services are served by containers. And what happens then is a request coming from a user typically gets broken down into many machine-to-machine requests. And that is what drives the east-west traffic significantly. As you can see, this chart shown by Facebook, where the amount of traffic that is machine-to-machine is much, much higher. It's orders of magnitude higher than user-to-machine. What that means is in this architecture, you may have containers or VMs that are talking to each other, providing these microservices that reside from one corner of the data center to the other. So the I/O has to span, has to go through various tiers of the network. And at every tier, latency is important, bandwidth is important. Okay? The other thing that is happening in application space is there's lots of data being created and lots of analytics being done. And they are being done through use of data lakes. Data lakes are data repositories of structured and unstructured data. So as a result, there's a lot of data movement. And to do data movement, you need high performance network with low latency. And increasingly, as applications are served from the cloud, there is increasing focus on availability and performance. So the overall impact of these applications and these new architectures, microservices architecture, is that the network needs to provide higher performance, bandwidth, lower latency, and they need to be highly resilient. Okay. Let's look at now evolution of compute. We know that Moore's law has come to an end. There is more and more of distributed compute, where you take a computing task and distribute it among various nodes. So rather than scale up, there is more scale out computing. And as computing happens in the scale out fashion, there's a lot of data movement happening between these compute nodes. And you want to make all of that happen without burdening the CPU. And as a result, RDMA is used, remote DMA is used. So you need to be able to support that in the network as well. We also see more and more focus on accelerators, NIC offloads, smart NICs, and more recently, these are also known as DPUs. You can see examples of them in AWS with Nitro, and the Google has their own, and each one of them is pumping a lot of traffic. As you can see, Google has announced 50 to 100 gig virtual NICs coming out of certain types of VMs. AWS has announced 400 gig coming out of some of their AI instances. VMware also has a project called Monterey, where they are going to support these accelerators and offloads. If you look at servers, the CPU evolution, people are putting more performance, more I/O, more memory. You can see them in the announcements coming from whether it's AMD's EPYC or Intel's Ice Lake announcements recently, as well as from ARM processors. Another emerging processor type is the GPU or the accelerators. So huge amount of focus on that, whether it's NVIDIA's A100, DGX A100, or even Microsoft. At their Ignite conference last year, they talked about disaggregating GPUs from the CPU so that there is better utilization. Okay? And PCI, CXL continue to drive higher performance. All of this means from a network perspective, there's going to be more performance, bandwidth, you need lower latency and robust RDMA. Let's look at storage. Storage with IoT, with autonomous vehicle, with mobile phones, videos, there's a huge amount of data being created. And more data means more processing of the data, more data movement. Second, the storage is no longer residing over traditional networks like fiber channel. It's all going over Ethernet. It's disaggregated storage, whether you look at files, blocks, or objects, EFS, EBS, or S3. I mean, this is not just at AWS, but in all clouds, everything is going over Ethernet. Also, if you look at the storage building blocks themselves, there is increasing use of flash and SSDs. They provide lower latency, faster access. So therefore, the network needs to reciprocate as well. And not just PCIe-based SSDs, but there is NVMe over fabric. So storage is going to ride over Ethernet and be served. Not only that, there are SSDs that are going to be connected with their controller to Ethernet itself directly. All of this means that the network has to be higher performance, has to have higher bandwidth, low latency, and deliver robust RDMA. Let's take a look at AI. Okay, this is an emerging field. The people are focusing quite a bit on it. Now, the infrastructure for AI looks like the following. You have GPUs or AI accelerators sitting inside some chassis and then connected to the outside world, either using a traditional Ethernet network that goes in and gets the data that is needed for AI, as well as there is a network to communicate between these AI nodes or GPUs, which is the AI ML network, and that is used for gradient exchange. What is happening with AI is you're continuously getting bigger data sets. You have more complex models, more parameters. As a result, it needs big infrastructure that spans multiple racks. So you can see that whether it's with TPUs which span multiple racks, 8 racks it goes, or you can look at the super pods for DGX. Okay? Now, the traditional network, as I talked about, is critical for data ingest. AI is fueled by data, so it needs to ingest a lot of data. And you can see that, for instance, AWS introduced 400 gig NICs for their AI instance so that it's able to ingest that data and process it. Now, the AI network that we spoke about is used to communicate between these AI nodes. So whether you look at, say, TPUs or A100s, each one of those nodes has big fat pipes. Collectively, each one of them has 2.4 terabits of connection between each other, often connected through a mesh. And that is used for doing gradient exchange. So you do compute, and then you exchange gradients. And you don't want the network to be the bottleneck. So network plays a key role. And more, we see that while the network can be built with proprietary PCIe, NVLink, or Ethernet, we see rise of Ethernet, RDMA, Rocky, being used to connect between these. So Habana, TensorTorrent are good examples where they are using Ethernet to communicate between these AI nodes. So net-net, the implication is for AI, you need high performance, high bandwidth, low latency, and robust RDMA. There's a tremendous amount of focus on power. If you look at any one of these cloud companies, they have committed to either being carbon neutral or being carbon negative. Okay, so huge amount of focus on reducing and becoming green. Second, power influences the number of servers that you can put in a rack, which influences also the configuration of the Tor switches, as well as other switches that are typically racked up in the leaf and spine. The other interesting point that Microsoft, as well as others, have pointed out is that power as a networking consumption of power as a percentage of total power is increasing. And they want to get that in line. So hence, huge amount of focus on being power efficient in networking. There's also a big focus on having these large scale data centers because of the digitization efforts, 5G, IoT, lots of data, lots of compute is going to these cloud and edge data centers. Each one of these cloud data centers have, as I said, 100,000 plus servers, which means there are thousands of switches. So the cost and power gets magnified at scale. And with that large a scale, you need to simplify operations. And to do that, you need telemetry and automation. Also, to be able to utilize all the resources within the data center, you want to have non-blocking networks so that you can do compute, you can talk to each other and use all those resources effectively. So the net of that is all of those drivers influence the requirements, which means you need to have higher performance with higher radix, you need to have lower latency, you need to have lower cost and power per bit, and you need to provide deep analytics and automation. Now let's go look at how switch solutions and the optical solutions are going to address these needs. As you can see here in this chart, the industry has been working to drive higher performance. Over the last 10 years, you can see that switch silicon and switches have come out at a regular cadence of every 2 to 3 years, starting from 10 gig SerDes-based switches to 25 gig SerDes switches to 50 gig SerDes switches, and very soon 100 gig SerDes switches. And another interesting point to note here is that all of these switches are all 1RU. 1RU form factor is the most popular switch that is being deployed. And it's because it delivers the best economics, it's optimized for space, for power, and it's easy to deploy. And this is not going to stop at just the 25.6T switches with 100 gig SerDes. There is roadmap for even 50 plus and 100 plus T switches as well. Now, as you increase the capacity and radix, there are compelling advantages that customers get. And that has to do with lower latency, power, cost, and complexity. Just as an example, if you see today, 256 port 100 gig radix switch that is made up of 6 12.8 T switches, all of that can be replaced with a single 25.6 T switch. And what this means is there is 6x reduction in switch silicon. There is a 3x reduction in latency because instead of 3 hops, you have just 1 hop. Because of the reduction in switches, it is lower power and lower cost. And not only that, it also means simpler software because instead of 6 control planes versus 1 control plane, as well as 6 management planes to 1 management plane. And we at Innovium have focused on our ultra-efficient Terralinks architecture to deliver the lowest latency and lowest power for each of these generations of switches, not just at 12.8, but at 25.6 and going forward as well. Now let's look at kind of the roadmap beyond 25.6. So here I show 51.2 T switch that will continue to use 100 gig SerDes and will interoperate with 800 gig modules. These are optical modules that today use 100 gig optical lambdas. They use the same 100 gig optical lambdas as ones used by the 400 gig DR4, FR4 kind of optics. And in the future, these optics will go to 200 gig optical lambdas to reduce cost and power further. And then if you look at switches beyond that, the 102.4 T terabit switches, they will use 200 gig SerDes and will operate with 1.6 terabit optical modules that will use 200 gig optical lambda. So that's the future where we are going in terms of the switch silicon. Okay. You can see the SerDes deployment expectations from analysts. You can see that analysts are expecting, this is report from 650 Group, that the 100 gig SerDes based products will expect to see product ramp in 2022, and it becomes a significant portion of the market. And then somewhere around 2024-ish is when 200 gig SerDes based products are going to be available. Okay. When you operate data centers at scale, one of the things that you want is richer telemetry and analytics, and that is to enable simplified operations. What happens when there is a congestion or there is microburst is you could start to see packet delays and drops in the network, which impact application performance. When such an event happens, what the network admin wants is he wants to find out where the delays are happening, where the drops are occurring, which applications or flows are getting impacted. And even better, is it possible for him to prevent them? So to provide all of this, you need rich telemetry and analytics coming from each one of these networking elements. That helps resolve any of the network issues, as well as it helps enable automation. And when these switches run at terabit speeds, you want all of that data to be available from the hardware running at line rate. And you also want these to be correlated to applications. So as you can see in the picture on the right, in our Teralink switches, when these packets come in and you start to see queue build up and packets start getting delayed, we are able to capture those. And after a certain point, if the buffer gets exhausted, you have to drop those packets. We are also able to capture those. and provide all of the analytics to the telemetry applications so that you are able to simplify operations. And telemetry is not just important for the networking switches, but also important for optical modules. Now, let's look at how these switches are connected in the data center. So it's copper within the rack. So when you connect the switch, the servers and storage to the top of rack, it's mostly copper. And if you look at the evolution of copper within the rack, as you have gone from 25 gig NRZ to 50 gig PAM4 to 100 gig PAM4, the distance, the reach has reduced. Okay? So it becomes a little bit of a challenge within the rack. And as a result, some customers are looking not at just DAC, but in active copper components. So using active copper cables within the rack as well. All connectivity beyond the top of rack is all optics, today using pluggable optics. And the type of pluggable optics used is determined by bandwidth, the type of fiber, whether single mode or multi-mode, the different types of reaches, or whether you want single or multiple fiber pairs. And customers today are using connectivity either between 100 gig to 400 gig. And what I show here are some popular flavors of optics. So to connect between top of rack to the leaf, people use active optical cable, AOCs, SR4, PSM4 for 100 gig, moving to the 400 gig AOC, SR8, DR4 to DR1. These are quite popular. And if you look at between leaf and spine, you have CWDM and PSM for 100 gig, FR4, DR4 for 400 gig. Now, for connectivity to the outside for DCI, you have longer reach optics. So people use CWDM4 or FR4 for up to 2 kilometers, depending on whether it's 100 gig or 400 gig. You use LR4 or LR8 or LR4 for up to 10 kilometers. And then beyond that, it's coherent optics, which is available now in 400 gig ZR modules that go up to 100, 120 kilometers. So that's kind of a quick synopsis of what people are using today. Next, customers are looking at 800 gig. And so that is what will be available with the 25.6 terabit generation of products that use 100 gig SerDes and 100 gig lambdas. Some customers will also deploy 200 gig, but that's a fairly small set of customers. Most large customers that we find are looking to go even beyond 400 gig, and hence 800 gig is important. With that, let me now hand over to Hugh. Hugh is going to cover the various kinds of optical connectivity solutions and look at it in depth. Hugh?
Thanks, Amit. So Amit did a great job of talking about the data center architecture and where switches fit into it, and summarized with how optics are enabling the longer reach connections going forward. And as he also explained, as data rates continue to go up, as we go from 28 gig to 50 gig to 100 gig and eventually 200, the physical distance that can be driven with copper is reducing quite dramatically. And so that's driving certainly optics between the racks, but eventually as we get to higher data rates, optics may even be required within the rack. And so what we've seen over the lifetime shown here on this slide is that with each generation of switch, as the capacity of the switch goes up, the optics capacity has to follow. And the reason for that, quite simply, is that there's a practical limit in terms of how many SerDes can be integrated into the switch. And so because of that limit, it's not possible to simply increase the bandwidth by adding more SerDes, but the data rate of those connections needs to continue to increase on the switch side, and the optical modules need to compensate for that and adapt to the higher data rates. And what that is driven, as you can see here, is that in each subsequent switch generation, which is doubling every device to device, that the optical module capacity has also doubled. Quite often there are interim solutions which support a lower data rate on the electrical or host side and a higher data rate on the optical side. But eventually the data rate on the host side needs to increase as well. And so we anticipate that there's going to continue to be a high demand for pluggable optical modules, the traditional optic modules shown here, which go into the front of the switch device. But if you could do a click to the next slide. But what we're going to talk about today in terms of next generation is what's called co-packaged optics. And this is where the optics and the switch device are packaged much more closely together in order to primarily drive lower power. Next slide, please. So digging into the optical modules a little bit more in terms of what are the components that go into this. And this will be important when I get to the subsequent slides and talk about some of the future options for configurations of optical connections. Starting from left to right, what you have is what's called the Dsp chip. PAM4 is the signaling methodology that's used at data rates higher than 28 gigs. So at 56 gig and beyond went to PAM4. And what the Dsp chip does is it takes the electrical interface from the host and converts that to a driver which can adapt to the optical channel. Optical channels have different losses, different compensation is needed than what's needed on the electrical side. The next thing, again, going from left to right, there's a set of controllers. Typically there's a microprocessor which allows the host to configure the optical module. There's a controller which is primarily an analog controller, which is related to the silicon photonics. So it's driving the different voltages and so on required to control the silicon photonics. And then there's often a PMIC, a power management IC, which just provides the different voltages for all the devices within the optical module. The next set of devices on the transmit side is what's called a driver. So this takes the low swing output of the Dsp chip and drives a higher voltage swing device, which is necessary to drive the actual optics drivers. Continuing with the transmit path, the next thing is the laser, which generates the light, and then the silicon photonics IC, which is what modulates the laser light to create the signal that goes out over the optical fiber. On the receive side, coming in, you have the photodiode, which is what senses the light and turns it into an electrical current. Then you have the transimpedance amplifier, which takes that current from the photodiode and creates an electrical signal, which can be received by the PAM4 DSP, which then transmits the data back to the host. Next slide, please. So optical modules have been around for a long time. They're a tremendous solution. They're very flexible because typically within a switch system, you can plug in a wide range of different optical modules into a given port, because all of the SerDes in the switch not only support the highest data rate, but also legacy data rates. And so if you're a installation which has a wide variety of different connections, some legacy switch boxes and so on that you need to connect to, optical modules are wonderful because you can support all of those legacy connections as well as supporting the latest and greatest highest bandwidth technology. But if you're a data center operator like Facebook, the challenge that you have is, as Amit described, power. You've got these very large data centers. Often the capacity of what can be installed in the data center is not limited by the physical footprint, but it's limited by how much power you can get into the building. And what the data center operators get paid for is the computes and storage, which on this set of pie charts on the right is the blue section. It's still the predominant consumer of the power. But what we see is generation to generation, more and more the networking all of those connections between the different servers and switches within the data center are continuing to consume a bigger slice of the power. And so if you're a data center operator, you can think of that as a tax, because you're not getting paid for that. You don't get paid for the data movement within the data center, you get paid for the computes and the storage. And so there's a strong incentive on the part of the megascalers to continue to try to reduce that orange slice in order to devote more power within their building to the blue part, which is what they get paid for. Next slide. And so to address that challenge, the industry is looking at a number of different alternatives to the current pluggable optics module. So what you see on the top is the current situation where the switch chip is inside of a package and it's just sitting on a board, a main board within the switch. And it's communicating over a channel which is a few inches long to connect between that switch and the optical cage on the front panel. And then within that optical cage, you have the optical module with all of the components that I described a minute ago. Going forward, in order to reduce power, what people are looking at is different alternatives to bring the optics closer to the switch. And by bringing the optics closer to the switch, you can use a lower power SerDes in both the switch device and in the optical module. And since it's a lower power SerDes, you're saving on the power that's consumed by the communications between the two. So the first alternative that's being looked at is what's called NPO, or near packaged optics. In this case, the switch is still inside of a package, and that package is mounted on a mezzanine card. And on that mezzanine card is also a socket which will accommodate optical tiles. The components within the optical tile are essentially the same as what I described earlier in the optical module. The main difference is that because the physical distance between the switch and the optical tile is less, you can have a lower power SerDes on that host side. In this case, what we're calling XSR plus. So XSR is a industry standard defined by the OIF. It stands for extra short reach. This particular configuration probably exceeds the reach of an XSR SerDes. So there's some talk of defining an enhanced version of that, which is called XSR plus, which is what I've shown here. The next option is one step farther, which brings it even closer. In this case, you have a very large package substrate. The switch die is mounted directly on that package substrate, so there's no package just for the switch. Also on that substrate are the sockets that would accommodate the optical tiles. The optical tile here is essentially the same as the one that was shown in the near package optics alternative. The only difference being that things are closer together, and so you can use a standard XSR SerDes, about a 10 dB channel loss between the switch and the tile. And then the fourth option that's being talked about is what's called direct drive CPO. In this case, the OR, or optical reach SerDes, is integrated into the switch die. It communicates over a package substrate to the optical tile. The optical tile has no DSP in it, just the driver and TIA, and then the optics. Next slide, please. And so again, the motivation for this is the power reduction that can happen. So what this graph shows is the dark blue at the bottom is the core of the switch. And in this case, that's a constant. We're assuming the same capacity of switch and the same process technology, so that doesn't change between the variants. The light blue at the top is the power consumed by the optics themselves. Sorry, excuse me, the gray in the middle is the power consumed by the optics themselves. And then the light blue at the top is the power consumed by the communications between the switch and the optics. And what you can see is that by bringing the switch and the optics closer together and using these lower power SerDes for that communications channel, you can get a dramatic reduction in the overall power. And our estimates say that either for the XSR CPO or the direct drive CPO, either one of those implementations deliver roughly 30% power savings over the traditional pluggable optics module solution. And because of that power savings, there's many different types of applications where this could be a compelling solution. The first one is in the switches. So switches communicating to the servers will definitely be the first place where that co-packaged optics gets adopted. It could also be used in the NIC cards that the servers are, the switches are communicating to that are plugged into the server. And going forward, it's compelling for AI and high performance computing, and even within disaggregation of future systems as server chips start to get disaggregated. To show a picture of what this looks like, what you have here is the green is the package substrate that everything sits on. In the middle of it, you have the switch die. In this case, we're assuming a 51.2T generation switch. And then surrounding that on the edge of the module are 16 CPO modules. Each one sits in a LAN grid array socket, and each module is 3.2 terabits of capacity. So one other difference between this solution and a pluggable is that the equivalent generation of pluggables will be 800 gig. This is 4 times that capacity in each optical module, or 3.2T, which also allows us to save some power within the optics by having a higher level of integration within the optical module. And so if we compare these alternatives, everyone has some advantages and disadvantages. The standard pluggables have the advantage that it's a well-known solution with the industry. It's very well established. It's very flexible. And one of the big advantages is that the configuration of when the optics get mated with the switch happens in the field. You install the switch in your rack, and then you plug in whatever optics you want in the front panel. As we go to NPO and the different CPO alternatives, the advantage that they have is, as I described, much lower power, about 20% reduction in the case of NPO and 30% in CPO. They bring some complexities, which I'll talk about in a minute. One of them being, back to the configuration, is that it's not going to be possible for this to be configured in the field. It's something that'll have to be configured at the time of the system manufacture. So if you have to replace an optical module or something, it's a little bit more cumbersome, but the advantage that you get from that is the fact that it's much lower power. On the bottom row of this table is related to the standards. So there's standards which exist today which define all of the pluggable modules. There's currently efforts underway within OIF and other forums to define CPO. And this is the XSR CPO. The disadvantage to the direct drive is that there is no standards organization associated with that today. It might be possible in the future, but what we're seeing from our customers is that they're demanding a standards-based solution. And so the CPO or NPO based on XSR is a much more attractive option for them today. Next slide. And if you look at the history of the industry, there's many examples that show that standard-based open solutions are much preferred by the customer. They provide choice to the customers. They allow multiple suppliers to innovate around that standard and better drive the technology and ultimately provide a lower cost of ownership to the customers. You can look at this from the applications point of view, storage arrays, server solutions, or networks. And so we feel strongly that having a standards-based solution is going to be critical to the success of any optical solution, whether it continues to be pluggables or as we move to CPO-based solutions. Next slide. Now, talked about the advantages of co-packaged optics. It, however, is not without its challenges. There's business model challenges. For instance, as I mentioned today, the way things work is the end customer buys the system from the switch supplier. They buy the optics from the optical module supplier, and they put them together at the point of installation. As we go to co-packaged optics, that integration is going to happen at the time of system manufacture. And so there's some business model things about who buys the optics. Does the Swiss system provider purchase the optics and then assemble it, or does the end user purchase the optics and consign them to the system integrator? Those are things that have to be worked out. We have to define the form factor and the pinout for these new modules. The power and cooling has to be worked out, how it gets integrated to the system, how it gets serviced. And then finally, what electrical interfaces go between the switch and the optics are all things that are being worked on. These are all solvable problems. I don't think that any one of them is an obstacle to the adoption of co-packaged optics, but they are things that the industry needs to work out for it to be successful. So I'll summarize. So as Amit described, the compute plus storage is driving forward. There's constant demands for higher bandwidth. There's constant demands for lower power. People like Microsoft have stated a goal to be carbon neutral or carbon negative in the not too distant future. And so addressing those power and performance challenges, as well as adding the telemetry features and the latency, is critical for future solutions. The things that we've talked about here, both on the switch side and the optics side, are geared towards addressing those emerging requirements. We believe that pluggable optics will continue to have a life. Co-packaged optics is not going to solve everyone's problem. As I described, pluggables still offer a lot of advantages in terms of flexibility. But the large-scale deployments within people like Microsoft and Facebook and so on will adopt co-packaged optics because they have much more control about their installations and they have a strong desire to reduce that power. One thing that was also mentioned is the need to have common components and technology wherever possible between these two. Co-packaged optics can't be a brand new from scratch development on the switch side or the optics side. And so the roadmap that they're working on right now does leverage many, many components and many technologies between the two. So co-packaged optics is really an incremental development effort. It's not a brand new development effort. And then finally, because of the choice that it provides to customers and the security of supply that having multiple sources provides to customers, we strongly believe that whatever standard is going forward has to be based on an industry standard with multiple suppliers for each of the elements within that solution. All right, thank you very much.
All right, fantastic. Well, thank you both for presenting this. We have quite a lot of material there. By the way, these slides will be available for everybody to download, both at the DuPont Silicon Valley website as well as through the COBO website. We have a couple of minutes here to go over some questions that have come in. So first, Hugh, I think if you could back up to slide number 23 first. So on this slide, I believe you said that there was a practical limit to how many SerDes can be inserted into the switch. Why is that? What causes that limit? Why couldn't we just continue to scale it?
Yeah, good question, and I'll let Amit chime in as well. But the size of a given device, first of all, if you're building a monolithic device, the size of that device is limited by what's called the reticle size. So semiconductor suppliers like TSMC can only build a certain size of monolithic silicon, and roughly that's about 25 millimeters by 33 millimeters. And so the SerDes have to exist on the edge of that device, and you only have so much edge space available. And so it's just there's a practical limit to how many SerDes you can implement on a given switch. Now, some people are moving towards other configurations with chiplets that sit around the core device. And so that allows you to have some more silicon area because you're dividing it between the core switch and the chiplets that sit on the edge. But then you need some kind of bus that communicates between the core switch and those chiplets. And then ultimately that becomes a limiting factor in terms of how much bandwidth you can get off of that core switch die.
Yeah, I think Hugh covered it quite well. It's the beachfront real estate that is necessary for SerDes. That is the limiting factor.
Okay, great. Hugh, could you move on to slide 24, please? So here the question is about how many separate electronic functions, the DSP, the controller, et cetera, are on separate chips. And could you not integrate those into a single monolithic chip?
Yeah, so that's a good question. Some of the things on this diagram are being integrated. So one example is that many of the latest DSPs from Inphi integrate the driver. And the reason is that the driver is still a CMOS device. It's, as I mentioned, it's converting the typical lower voltage swing output from a SerDes, usually in the range of 0.9 volts peak to peak, to a higher swing output up to 3 volts. But that function can be implemented in CMOS in the same process technology as the DSP. The DSP typically needs to be in the most advanced process technology because of the density of the logic that's within it, and also the performance of the interfaces that needs to go on it. So today those devices are in 7 nanometer and they're rapidly moving to 5 nanometer. Other components here can't really be accommodated in that process technology. Things like, let me use as an example, the silicon photonics. Silicon photonics typically are lagging process technologies from a logic point of view. So today you're looking at 40 nanometer is the leading node for silicon photonics. And it'll be a long time before silicon photonics get integrated into an advanced node like 5 nanometer. Okay. So practically speaking, you can't combine them. Other devices, photodiodes are non-CMOS. Some of the things like the controller or the PMIC just don't need to be in the most advanced process technology, and it's more cost efficient to develop them in older process nodes.
Okay, fantastic. If you could move ahead to slide 26. Yeah, so here you're showing the 4 different options. First, is it technically more difficult as you go from top to bottom in terms of manufacturability, integration?
The answer is yes. The first one with pluggable optics is well proven today, so there's no manufacturing issues there. NPO is a little bit of a step forward in terms of the complexity, but the materials used are the same as they are today. The main complexity actually comes in the optical tile because, as I mentioned, the capacity of the optical tile is 4 times what the optical module is, and the physical space is actually smaller. So we get into 3D stacking and through silicon vias and things like that. So the complexity of manufacturing the optical tile is greater than the optical module. And then as we go to the final 2 options, the complexity there is package substrates today are in the range of 70 millimeters on a side for a very large device. These implementations will require package substrates that exceed 100 millimeters on a side. And so the complexity of building that large a package substrate and the cost associated with it becomes a factor in the final 2, number 3 and number 4.
Okay. We're just about at the top of the hour, but we have some more questions coming in. So I'd like to hold this open so we can take a couple more of these questions. So Hugh, on this slide for the direct drive CPO, what are the real advantages for the customer? There's some people who are asking about that. Why is direct drive CPO solution, a viable option from the customer perspective?
Well, I'm not sure that the feedback we've gotten from customers is that since the direct drive solutions that are being talked about are proprietary, it's not desirable to the customer. The customers very much want a solution which is modular and from which they can have multiple suppliers for each of the components. One other aspect of the direct drive that I didn't mention is that As you can see with the optical tile, the optics components are assembled on a package substrate, and that package substrate goes into a socket on the switch substrate. With the direct drive, because of the complexities of driving that optical channel from the switch directly, the optics need to be soldered down onto the package substrate. And so it's not configurable, and there's also serviceability issues with that, because if some component breaks, you have to throw the whole thing away.
Yeah.
There's no option to replace the optical tiles if something should fail. And so at least the feedback we're getting from customers is that the direct drive is not a very desirable solution for those factors.
But the power savings is the thing of interest here, right? If it can be implemented.
Our analysis shows that the direct drive, give or take a few percent, is essentially the same power as the XSR-based CPO. There is no dramatic power saving by going to direct drive.
Okay, here's a question. Will co-packaged optics be a thermally viable solution with the ASICs and the optics so close together?
That's a good question. That's one of the challenges. Maybe Amit can give his perspective on that as well. The power density has definitely gone up because you've moved everything closer together. The total power has gone down. So, I mean, it's a solvable problem, but it is something that needs to be sorted out. So that's why it is one of the challenges on this slide.
That is right. So even though overall total power goes down, the density of power, it's concentrated in a small area. And so certainly solvable. And, we are partnering with the system partners to be able to develop systems towards that, but it is a challenge.
Amit, can you provide some thoughts on server disaggregation as it relates to help with reducing networking power consumption?
Can you repeat the question, please?
Can you provide some thoughts on server disaggregation as it relates to helping with reducing networking?
So server disaggregation has been discussed for quite a while now. If you look at a server consists of CPU, memory, I/O, right? And also now some co-processing offloads for either networking or for AI functions and so on. Now, I think as I see it, the next step would be to disaggregate, the GPU AI functions. And that is something that if you follow the industry, Mark Russinovich from Microsoft has already talked about it last year, where they want to disaggregate the AI GPU type of functions from the server. And that is one of the use cases for perhaps the co-packaged optics. I think disaggregating memory and so on, I think they are a bigger challenge in terms of physics, laws of physics. I mean, that I think will take some time, but at least some of these functions like, offloading of the AI functions, GPUs, that, at least is in the near-term horizon from a server disaggregation perspective.
Amit, there was also a question for you about storage. When you're talking about storage, you said that everything is Ethernet. Does this mean that fiber channel is dead?
So I think, it depends. So clearly, if you look at the cloud and the new deployments, clearly everything is moving to Ethernet. In the enterprise, some of those guys will continue to use fiber channel. It's like, mainframes. Mainframes have not been the focus for the last 20, 30 years, but there are mainframes still. So fiber channel in the enterprise for certain applications would stay. But if you look at the overall kind of focus of storage, it's NVMe over fabric. It's in the cloud. It's pretty much all storage from all cloud providers are all Ethernet based. So I think as I see it, fiber channel is certainly going to continue to go down, and the future is all about Ethernet-based storage.
Two more quick questions for Amit. And if you could go to your slide 21, please. So here, I think you were talking about telemetry. And the question is whether this evolves to be an open standard-based way of doing telemetry, both in the switching and then, I guess, extending to the optics side as well.
Right. I think, clearly customers would prefer to have open standards-based telemetry. And there are certain efforts going on in the industry, right? When you look at in-band telemetry, there are standards that have evolved. Certainly, I think the APIs between the telemetry engines or the collectors to the switches, those will and have been standardized. So clearly, there is a move towards standardization wherever possible. And I think depending on what type of telemetry can be provided by the different switch vendors, clearly the goal is to provide open ways of doing so. But that is certainly an industry trend that you can see some of those efforts in the standards bodies, in some of the NOSes and so on.
Okay, fantastic. And final question for your next slide, slide number 22. I think here you were talking about copper connectivity, and the question is how does that continue to scale? Is that going to move up on even shorter distances, or are we seeing at some point an end to it?
Jim, can you repeat? I didn't quite get
it. So the question is on the copper side within the racks. Is it primarily, first of all, is it primarily a cost consideration? And also, will copper continue to scale?
So I think clearly copper is the cheapest, the most cost-effective way to connect. And that's why within the rack, copper has always been used. Now, as we see with higher speeds, the distance, the reach for copper becomes a challenge, right? As we look to go to 100 gig PAM4, copper can only go up to 2 meters. Now, if you have need for reach to be more than 2 meters, that's a challenge. So clearly there'll be ways in which customers may not put the switch at the top of the rack. Maybe they'll put it in the middle of the rack so that the reach between these servers within the rack can be within 2 meters. So that's one possible way. But if they do need longer reach, copper alone, passive copper may not be able to meet it. So there are efforts to do active copper and potentially for higher speeds, even optics within the rack. So it depends on the deployment, that depends on what the reach requirement, but clearly copper is always preferred given it's more cost effective than optics. Right?
All right, fantastic. Well, with that, let's bring our webinar to a close. I'd like to thank both of our guests, Amit and Hugh, and also to our sponsors, the DuPont Silicon Valley Technology Center and the Consortium for Onboard Optics. This webinar will be available within a couple of days for people to share with their colleagues or to review, as well as the slide decks. So thank you everyone for joining us, and we look forward to seeing you again soon.